Hello, everybody, and welcome back to another lecture in Geography 340, Climatology. I'm Dr. Zach Hilgendorf, and in this lecture, we're going to be talking about our changing climate. Moving on from paleoclimates, this lecture and the next will focus on kind of contemporary climates, how we know they're changing, and then what that means for our future. So first off, how do we know that anthropogenic climate change is happening? There's a number of different ways. First off is just instrumental records of air temperature. We've been able to keep records of air temp for over a century, well over a century now, with just simple thermometers all the way through to the more advanced technology that we use today. And here we can see just a plot of the 20th century average, which is our zero line, and then temperatures anomalous to the 20th century average in blue for under that average, red for over that average. So we can see up until about 1940 or so, kind of lower temperatures than our 20th century average. Once we get to the 40s and on, so to our present decade, we're seeing just a widespread increase in global temperature anomalies to the degree of nearly a degree Celsius. You can see here in 2016. This trend is pretty consistent across a number of different methods. Instrumental records of ocean temperature are going to kind of give us a similar story. Here we can see three different graphs. The top above me, 0 to 100 meters depth mean temperature anomaly. So this is the first 100 meters of the water column on average. This is from the Ocean Climate Laboratory, whole collaborative effort between NOAA and the National Climate and Environmental Proxy groups. In the top right, that's ocean depths from 0 to 700 meters, and the bottom right, that is ocean depths from 0 to 2 kilometers. So just like in the air temperature, we're seeing the mean temperature anomalies increase. Here we're seeing just from the 1960s onward, up to the tune of about a half a degree Celsius within the water column, the upper 100 meters. So if you think about that, the colder, denser water sinks. We remember that from our ocean climate lectures. So here we're seeing kind of the first 100 meters is noticeably warmer and sinking or kind of soaking up most of the warmth. In fact, since 1970, 90% of global warming has happened in the oceans. Now, if we think all the way back to think about water and its specific heat, it heats up more slowly, it cools down more slowly, it takes more energy to heat water up, but then it takes longer to lose that energy as well. We're seeing the majority of our heating within our oceans. The first 100 meters up to about a half a degree, and the first 700 meters, 2/10 of a degree, and then in the first 2,000 meters or 2 kilometers, we're seeing up to a 1/10 of a degree averaged out over the entire aspect of the water column, which is pretty astonishing if you think that 2 kilometers down into the surface, we're seeing the impacts of kind of our warming ocean waters. Proxy climate data, that's where we spent a good chunk of the last week learning about different aspects of proxy climate data, from dendrochronology to ice cores to lake cores and and pollen data, pardon me. So we just know that these are indirect records of past climatic conditions. They preserved physical characteristics of the environment that can stand in for direct measurements of past climate conditions, proxy data, such as dendrochronology, looking at the annual growth rings of trees. For some tree species, we know that it's determined in part by average annual temperature or by precipitation. So here is a very famous graph. This is what we call the hockey stick graph. Now, this was made famous by Michael Mann, the author who you see cited down there, Northern Hemisphere Temperatures During the Past Millennium, Inferences, Uncertainties, and Limitations. So this hockey stick is kind of what we see across all of our proxy climate data, or most of our climate data, whether it's carbon dioxide concentrations, methane concentrations, temperature anomalies, the primary ones there. Now, obviously, Dr. Mann has been the focus of some ire Not everyone believes the hockey stick or gives credence to it, but over 97% of scientists throughout the world do believe in this effect. You can see that book there, The Hockey Stick and the Climate Wars by Michael Mann. Definitely an interesting one to look at, kind of talking about this signature that we're seeing indicative of global climate change based off of these proxy data records that we have. So moving into it next, how is anthropogenic climate change changing the planet? And that's where we're going to kind of spend the majority of the rest of our lecture here. First off, permanent ice is decreasing, whether that's in the Arctic, the Antarctic, the Greenland ice sheets, everywhere across the world, the ice sheets are decreasing in size. The Arctic ice sheet maximum extent was March 5th, or here we see it March 5th, 2020, 15.05 million kilometers squared. There we see it in September of 2020. So this is just 1 year that we're looking at. Here we can see Arctic sea ice extent. This is throughout the year. This first line we're looking at is the 1981 to 2010 median, the climate 30-year record. And here we can see this is 1983 through 1979. There we are in the late 2000 teens into 2020. Give this site a look if you want to learn a little bit more about sea ice changing. In this graphic, we can see kind of changing sea ice. So this is the annual Arctic sea ice minimum area. So we can see this from the mid to late 70s through kind of our present time. Shouldn't surprise you, is what we've been talking about now. We're just seeing a consistent decrease. A couple blips now and then where we see an increase. There are annual cycles and seasonal cycles to observe, but by and large, we're seeing just as drastic of a decrease as we are anything else. Till we get to our present. Land ice is changing pretty drastically as well. In mountain or alpine glaciers, we see it all over the place. You've seen these pictures before. Documentaries like Chasing Ice really do this justice. Here you can see a glacier, or just a river of ice flowing over land. We have an accumulation zone, an ablation zone. So accumulation is where the glacier is gaining mass. The ablation zone is where it is losing mass through melting or calving, so chunks of it are falling off. Glaciers grow or thicken or lengthen when the annual accumulation is greater than the annual ablation, or shrink when the opposite is true. An annual ablation is greater than annual accumulation. So here we can see mountain or alpine glaciers in the Himalaya and Tibet, the Andes, southern Alaska, western Canada, and northwestern United States. Here we can see Boulder Glacier in Glacier National Park in Montana in 1932. And here we can see it in 2005. Here we can see the Muir and Riggs glaciers in 1941. So here we're looking northeast on the southeastern side of the White Thunder Ridge. There we can see it in 2004. The Peterson Glacier, the 1920s to 40s, somewhere around there. Here we can see it in 2005. This is a global story. You can see the Columbia Glacier in Alaska is another pretty famous one. This is in 2009. Retreated 6.5 kilometers from 2009 to 2015. Here we can see glacial mass balance, or mountain glacier glacial mass balance from 1980 to 2015. 41 reference glaciers monitored by the World Glacier Monitoring Service. The story is ubiquitous. We're seeing a decrease, a drastic decrease in the mean specific annual balance in glaciers across the world. The same story can be said for our ice sheets. So here we're seeing ice sheets like the Greenland ice sheet, the Arctic ice, or the Antarctic ice sheet. The Antarctic ice sheet contains 88.24% of Earth's permanent ice. Greenland contains another 11.14%, whereas alpine glaciers only contain 0.62% of Earth's permanent ice, just to give you some scale here. So we measure these using things like the GRACE Recovery and Climate Experiment, or GRACE satellites, or sorry, Gravity Recovery and Climate Experiment. 2018 to the present, the GRACE FO or GRACE Follow-On, which is just an additional satellite that was sent into orbit, basically looking at gravity changes on the surface. In Antarctica, this is what we see. A little bit of a gap there from when the satellites were switched over. You see that by the little gap in around 2018-19. But Antarctic mass of ice sheets in gigatons is decreasing. We see over 2,500 gigatons of ice lost from the early 2000s through the present. On average, about 148 gigatons per year. In Greenland, even more, 279 gigatons per year are being lost. Definitely recommend. Greenland is melting away. This is a pretty good Times article to read on just kind of what's happening there. Next one, sea level is rising. So here we can see kind of our average change in sea level in millimeters per year compared to the 1993 to 2008 average. Our long-term rate is about 1.8 millimeters per year. Since 2000, nearly double, 3.5 millimeters per year. So we ask then, what's causing sea level to rise? Well, a number of different things. The first is thermal expansion. As water warms, it expands. That is adding to sea level rise because it's taking up more space, right? Melting of our mountain glaciers, adding water. Melting of the Greenland ice sheet, melting of the Antarctic ice sheet. All of these things are adding water to the oceans and increasing our sea level rise. Weather patterns are changing. Climates are changing. So we talk about climate change. What does that even mean? Well, we know what a climate is. It's the generally expected weather, including seasonal changes based upon past weather observations and measurements. We've talked about this the whole semester now. It's driven by weather, produces the generally, or what drives weather and produces the generally expected weather that we call climate, the uneven distribution of thermal energy in the atmosphere, and seasonal changes in the distribution of thermal energy in the atmosphere. We saw this weeks ago in lecture 14, I believe it was, at the time when we were looking at global latitudinal variations in temperature. We're going to look at it again here. So this is starting in 1850, looking at human and natural drivers of climate change. And now that we've talked about so many different things, we look at global changes in the mid-stratosphere, the lower stratosphere, so the bottom or the second one down, surface temperature, and ocean heat content. And then we also can look at the Arctic ice area on the top right. Something important to note is, and I believe we've mentioned this before, very far back, if the changes in our climate were driven by cycles like the average solar cycles, right? Well, first off, we know that solar activity has been in a decline over the last number of years. But if that was true, and if it was based on solar, we would see all levels of the atmosphere being heated equally, or at least being heated at the same type of a rate. The troposphere, the stratosphere, the thermosphere, the ionosphere, all of these different layers of our atmosphere would be heating at the same rate. Why? Because that insulation is passing through all of them. So you'd expect to see that type of a change. What we see instead is preferential heating within the lower troposphere, along the surface. And that's driven by a lot of things, and we'll talk about those here in just a little bit. But the gist of it is that it's things like greenhouse gases and anthropogenic greenhouse gases, the addition of greenhouse gases, that are driving these changes along the surface, trapping more heat within our surface rather than in the stratosphere, for example. So we're going to play this one here, and we'll just kind of watch what happens. Just remember that the white line, if we look at the legend above my talking head here, are observations. So those are observed temperatures or observed conditions. The green represents natural drivers only. The red represents human drivers only. And the blue represents a combination of natural and human drivers. So here we're going to advance through the late 1800s. And everything's kind of holding pretty consistent for the most part. Once we get here to about the 20s, 30s, we start to see a change in our ocean content and our surface temperature, where we see nothing of the sort in our lower stratosphere and mid-stratospheric temperatures. Various changes, obviously, that happen, but they are trending towards a decrease in temperature anomalies, whereas our surface temperature and our ocean heat content are both doing the exact opposite and trending towards a quite drastic increase up to a degree or more in temperature. Our Arctic ice is doing the same thing as our mid-stratosphere and lower stratosphere temperatures. It's decreasing, but that's not a good thing because we're seeing the increase in our surface temperatures. Arctic ice anomaly, or Arctic ice area, is decreasing. We saw that in our previous video graphic. We see it in our own backyard. We look at climate trends. This is the Department of Natural Resources in the state of Minnesota. Minnesota's climate already is changing rapidly and will continue to do so for the foreseeable future. Temperatures are increasing, especially in winter, and larger, more frequent extreme precipitation events are occurring. You can see this is one of their expandable subsections here. Minnesota keeps getting warmer and wetter. Minnesota is warmed by 2.9 degrees Fahrenheit between 1895 and 2017, while getting an average of 3.4 inches per year wetter. When Minnesota has gotten warmer and wetter since 1895, the most drastic changes have come in the past several decades. Compared to 20th century averages, all but 2 years since 1970 have been some combination of warm and wet, and each of the top 10 combined warmest and wettest years on record occurred between 1998 and 2017. Although climate conditions will vary from year to year, these increases are expected to continue through the 21st century. Cold weather warming. This is another one of the drop downs they have. Most of Minnesota's observed warming has been when it's its coolest. Since 1970, winter has warmed 13 times faster than summer, and nights have warmed 55% faster than days. The frequencies of negative 35 degree Fahrenheit readings in northern Minnesota and negative 25 degree Fahrenheit readings in the south have fallen by up to 90%. We don't get as cold as we once did, and even though Minnesota will always see periodic severe cold spells, the long-term decline in cold extremes is all but guaranteed to continue. Here we're looking at Minnesota average winter daily minimums from 1896 to 2018. We're seeing the 10 warmest by the red dots. We see one in the 20s to 30s. The rest of them have been since 1980. We're seeing a average rate of change of 0.49 degrees Fahrenheit per decade of increase in temperature during our winter months. And we see that 9-year moving average of winter lows is just increasing. So we know that anthropogenic climate change is happening through things like instrumental records of air temperature and ocean temperature and proxy climate data. We know that anthropogenic climate change is changing the planet because we see things like permanent sea ice decreasing, sea level rising, and climate changing. In the next video, we're really going to dive into what we're seeing and why it matters. So we will see you in the next video, and I hope you have a great day.